Hello and welcome to this video about teaching elementary mathematics with our focus today is on problem solving. I'm Adam Petzel and this video is largely based off chapters 2 and 3 in the textbook Teaching Elementary and Middle School Mathematics by John Vandewalle, Karp, and Bay Williams. So in this video, we're going to explore what that really means, this idea of problem solving in math education, and take a look at problems versus exercises, different types of problem solving instruction in the classroom, and look at something called a three-phase problem-based lesson to help us think about enacting problem-based lessons in a classroom setting. So before we jump in, let me give a few tips when watching this video today. So first of all, go ahead and make sure and use the pause button and back and forward buttons on your device appropriately. We want to do that so that, one, that you can pause and take some notes and record key ideas during the video. Sometimes you may want to watch something again to clarify something or to hear how something was worded. But often I will ask you a specific question I want you to think about or to try. And when I do that, please use the pause button to pause the video and either think about the question or, if asked, to write something on paper. And sometimes that will be a math question. And so obviously in a video, I will be solving it shortly after it's posed, but to learn the most, it's often best when I ask you to try it yourself first and to think about how you would approach a certain question. And then I'll give one way to think about it when you unpause the video. And also, during the video, it's a good time to pause if something's unclear or you have more questions, to pause the video and jot down that question so that when we come to class, well, you have those fresh on your paper and can ask the questions you'd like to know. So with that said, let's begin. So to premise this idea of problem solving, let's remember that in math education, we have three big goals here in thinking about how students are going to engage with math in the classroom. We want students to engage and develop procedural fluency, which we know is being able to use strategies effectively, to be able to know procedures to get the right answer fluently and efficiently. But often when people think of math education, they stop there, about somehow getting the right answers. And today's education, the goal is so much more. We also see that at the bottom side, kind of the foundation is conceptual understanding. We don't just want to know how to get an answer, we want to know why things work. We want to be able to see how ideas connect, how different concepts are built on one another, and that math has connections to many different ideas. And then the idea on the top right, the application, really tells us that we also want students to be able to apply these ideas to new situations, to be able to solve interesting problems, to apply things to real-world situations. And so these things together help give us a more full view of what we'd like students to experience in our math courses. And all along the way, our emphasis is going to be on building mathematical reasoning and mathematical sense-making throughout our classrooms. So let's dive in with that in mind. So in our textbook, in chapter 3, our author really unpacks this idea of problem solving, which I'm sure we hear a lot about in math. Be a problem solver, solve all the problems for the homework. We just hear the word problem a lot, but what does that really entail? And in fact, when we look at the Common Core standards, besides all of the content-specific standards, they have these 8 standards for mathematical practice. These standards are supposed to be for students from grades kindergarten all the way through 12th grade, and they give an idea of while the students are learning math, the types of habits of mind, the types of thinking we want them to be able to do as they engage in math. And if you look at the very top one, and it's number 1 for a reason, it says make sense of problems and persevere in solving them. So right at number 1 in the Common Core standards, we see this emphasis on kids should persevere in problem solving and make sense of them. And I think we'd agree that sounds like a good thing, but again, let's unpack a little more of what that means. So one thing I want to note is the term problem. In math, the word problem is used in lots of different ways, and it's not always used in the way that we think of when we talk about problem solving. For example, I taught math for 10 years, and I'm sure I said a gazillion times, hey, for homework, do problems 1 through 10. Now, in that case, problems 1 through 10 may not actually be problem solving. So to start off, let's get maybe more clarity of words here. That in math, I want to clarify questions you might ask kids, that some might be math problems and some might be math exercises. So what do you think are the differences? Why don't you think for a moment and just think, what do you think the difference is between these two? Well, let's take a look. So I know for me, when I think about having a problem in life, it's because I don't know what to do next. Like if I have a problem, it's because I'm just not sure what the right path is to take and I'm trying to figure something out. And in math, that's the same idea. A true problem in math is when I look at something and I don't know how to do it right away. I need to play with it, I need to think about it, I have to develop a strategy. And that's a math problem. The definition here says any task or activity, question, for which the students have no memorized rules or methods. They often are characterized by having multiple solution methods and multiple entry or exit points. And the key thing there is it says again, they have no memorized rules or methods. Now they may use things they've learned, of course, but when they first look at it, it's not obvious just, oh, I should do this and I'll get the answer. Because in that case, it's not really a problem. Now, on the other side of that, we see exercises. And this is more like when I was teaching math and I would say do, questions 1 through 10 for homework. Usually, these were more of exercises. These are questions or tasks that, when I look at it, I don't know the answer, but I know I have a procedure for getting the answer, and I can do it fairly automatically or something that a procedure I'm learning to do more automatically. For example, right now, if I looked down the paper and I was working on some long division problems, and it asked me to do 476 divided by 91. I mean, right off the top of my head, I don't know the answer, but I have a couple procedures I could do to figure out that answer, and so it's not a problem, it's something I have to exercise. I need to just exercise a skill I already have to get the answer that I go through. And here's a big idea. I'm not trying to say one is good or bad here, or that we should prioritize one or the other. Both are important, right? Like we need exercises to build skills, to be able to practice those procedures, to think about things, and we know practice can be a good thing in many aspects of life. But often what we see in the history of math education is that too often classrooms really only deal with exercises and don't really give students much of an opportunity to really develop problems and problem-solving skills, where individually or collectively, collaboratively, they have to figure things out, to work together, to get new ideas, to have multiple ideas, to have more than one way of getting the right answer. And is the answer even right? I don't know. I got to think about it. And we like to see in classrooms that both are being used. So let's take a look at some examples here. So if you look at these four, I have 4 math questions here. I'd like you to think about, of these 4, which ones would you call problems and which ones would you call exercises? So pause the video for a moment and write down what you think. All right, well, let's take a look. It's a little bit of a loaded question, but let's talk through each one. So for A, okay, this is a general subtraction problem, and I think here we would probably agree that for most people this is probably an exercise. May not know the answer right away, but we have different procedures that we could probably do to figure out this answer, and so that's most likely an exercise. However, if you look at B, this is also a subtraction problem, still 3 digits minus 3 digits, but it says use the digits 1 through 9 at most 1 time each to fill in the boxes to make a difference, an answer, that is as close to 329 as possible. Well, this is still subtraction, but this is different. Wow, I'm not quite sure how to start this. Where should I even begin? I can only use the digit once. I know I gotta be close to 329. I'm gonna have to think a little harder here about my knowledge of subtraction and digits and strategy to solve this problem. I'm not sure what to do right away. So B for most of us would be a math problem. If you look at C, I'm going to actually go to D for a second. With D, it says find the volume of the sphere in the bottom right. And assuming we have a formula or some things here, again, this is an exercise. It's something that I need to practice to use the formula, but there's a right answer here. And if I know the formula, I know I can just plug it in and get the right answer. But compare that to C, where it says how many golf balls would it take to fill this room? Well, wow, that still is volume of a sphere. Same thing, still uses a volume formula, but that is a problem. Like, wow, I need to think a lot more. What am I going to have to do to figure that out? I mean, how are those balls going to stack? How many would fit across? How do I figure that out? Like, there's just another layer here of using my knowledge to solve a deeper problem. And so we see that. Now, here's kind of the rigged version of this question, though. Is you look at A. Now, I assume for most of us, A is a math exercise. But what if we went to a beginning 3rd grade class and told them that there was 821, let's say, milk cartons, for the school year and the lunch or for this week. And on the first couple of days, 357 were bought. How much milk was going to be left? Now, assume these kids hadn't actually learned, a lot of subtraction procedures yet. Now, for them, that would become a problem. Now, maybe they could use base 10 blocks. Maybe they could use some different types of visualization skills and pictures, diagrams to try and figure this out. But for them, that same question, which is an exercise for me to you, would be a problem for them. And that's a key idea I'd like you to just think about, that really, that depending on the age group and our own understanding, an exercise for one person could be a problem for something else. Well, now that we've clarified that a little bit, just the term problem solving, we know that we're talking about now students engaging in some tasks or questions that aren't just routine, that make them dive a little deeper to figure something out, to have to get some ideas. And when we think about this in a classroom, what does it start to look like? In Chapter 3, Van de Walle gives us 3 different versions of problem-solving instruction in classrooms and labels them with 3 different ways. He talks about teaching for problem-solving as one approach, teaching about problem-solving as a second approach, and teaching through problem-solving as a third approach. And so, looking at the Chapter 3, let's go ahead and take a look at the differences of how teachers implement these in the classroom. So teaching for problem-solving, well, what is that? Well, this is probably the most common means of problem solving in a classroom. And this just says that, well, in a progression of a lesson or a unit, kids learn procedures first. They learn the math skills and concepts first. They learn how to do some different things. And then eventually they use those skills to solve an interesting problem. Maybe it's that number 36 at the back of the chapter that actually is a much deeper question that can take a whole class period if we think about it, but or just makes the kids think a lot deeper. But again, the order here is important. Learn basic skills first, and then ask them to use skills to solve a problem. With the subtraction and addition and those things, I can think of a unit I was with where kids learned a lot of different types of skills, and then at the end of the unit, they had a typical plan a party type situation, and there was 20 kids at the party and all these supplies, and they were working on trying to figure out they had to keep within a budget and had to work figure out how do we order all the stuff we need and keep within the budget, and it just ended up having to apply their skills in really interesting ways and see if they could do that. So another example here, using the golf ball analogy from before, would be in this exercise, students would first learn about various volume concepts, right? Learn how to find the volume of a prism and the volume of a sphere. And then, after acquiring those formulas and skills, they would tackle a problem. For example, how many golf balls would it take to fill this room? Still a problem, but they have the prerequisite skills to consider thinking how they might start this off. And that's teaching for problem solving. I'm learning some math now for a problem later. All right, so that's just a common approach. But another approach Van de Walle talks about in our textbook is teaching about problem solving. And this is a little more nuanced. In this approach, the dialogue is a little different. The discourse is a little different. The classroom has a focus about problem-solving strategies in general, about general solving strategies, what it means to be a good problem solver. And then throughout the class, they use those strategies or approaches to solve a variety of problems. So let's think about this. So for example, George Poya is a researcher, I believe around the 50s, who wrote about problem solving a lot. And it wasn't just in math, it was in all areas. And just talked about that as humans solve problems, we tend to use these 4 steps. Phase 1, we understand the problem. We try and figure out what the problem is, actually define what it is, clearly understand the parameters. 2, we devise a plan to approach the problem. We think of what options there are, what types of options are available. And phase 3, then, we carry out the plan. We try it out. And phase 4 is we reflect. We look back. Did it work? Did it solve the original problem or not? Do we need to go back and revise the plan or try a new plan, or was there a better plan I could have done? And to reflect and look back on that approach. Now, this general approach we see in math education, teachers will take that and mathematize it somewhat. Like on the right side is just kind of an elementary classroom, little bulletin board that has kids think about being problem solvers, and about whenever they face a problem, they aim to understand, to plan, to do, and to check. And the focus on about problem solving is more of it's not math specific, it's more of a general idea about being a good problem solver. Now in class, we're going to watch the video that's linked at the bottom here. And this video is going to show us a school that embraced this, and they took their own approach, and they had the kids across elementary grades use this type of tool and checklist when they approached math problems of all different content areas of understanding, thinking, solving, communicating, and connecting. And they used a template like this, and we'll see, to solve a lot of different types of problems and built about the problem solving method. So again, this is about a general approach, not necessarily a specific math content. And again, the video, I think you'll like the video when we watch it this week. And when we think about general strategies, there are a whole bunch. Here's a list of some that we think about, just general strategies we might do when approaching a problem. And the more tools we have in our toolbox as problem solvers, well, the more problems we'll be able to attack. So let's take a look for a second. These are a few just classroom posters and things that teachers who have an about problem solving mentality often have this type of thing on their walls. They encourage general strategies that kids can use all the time and approaches. And over the past decade, I wanted to share kind of a newer strategy that works across many grade levels. It's a visual strategy and many different types of math content, and it's often called model drawing or bar models. And it's really increased in popularity. I bet some of you look at this and may know what this is. But we're going to use it across different things ranging from addition, subtraction, fractions, decimals, percents, ratios, proportions. All these things can be used with this general visual strategy. So let's try one together. Let's look at a general strategy that can be used. And so this was taken from a curriculum that, you don't have to use these 7 steps, but it kind of gives the kids an idea of here's how we can use this model drawing strategy. It doesn't matter what the content is, but it should work on many different things. So I'm going to go ahead and kind of model this with us together and then have you try 1 or 2 on your own, just for the sake of doing some math here in our video together. Okay? So let's take a look at what this model drawing strategy looks like. And here's our first question. Terrence and Ella have $121 altogether. Ella has $39 less than Terrence. How much money does Terrence have? Well, before I jump into model drawing strategy, go ahead and pause the video and solve this any way you want and see how you would approach it, and go ahead and get your answer for how much money Terrence has. Okay? Go ahead and pause the video and give it a shot. All right, so let's take a look at this with a model drawing type strategy. And to do that, let me switch screens and pull this one up right here. There we go, and make this a little bit larger. Okay, there we go. All right, and so I can see the problem. There we go. Sorry, gonna make this all the way bigger. There we go. Okay, perfect. Okay. All right. Well, first of all, if we go back to this, one thing that is just a nice strategy for thinking about questions like this is to have the kids really think carefully to understand the problem. And sometimes we can have them write what's called an answer statement. In this case, we want to clearly define what are we looking for, which is how much money does Terrence have. So an answer statement might look something like this. I might write, Terrence has blank dollars. And this would be, an answer statement, just knowing that when I can fill in that blank, I know I've solved the question. It just helps me clarify what it is I'm asking. And I can go back and read the problem carefully. Together they have $121, and Ella has $39 less. Well, let's take a look. So what I could do here is, using the model drawing is always bars. And so I might make a bar for Terrence and Ella. All right, and I don't know how much Terrence has, so I'm just going to make a bar that represents Terrence's money. I know Ella has $39 less, so I'll make hers just a little bit shorter because she wouldn't have as much money. And it says all together they have $121. All right, and Ella has $39 less. So there's, again, more than one way to approach this, but using these bars, I have this starting visual to think about it. What I might realize is I know this distance here would be $39. And I could even do this if I wanted. I realize, well, that means up here, Terrence would have $39 more than Ella. Like, that would be the difference of their money. So what I might do is realize, well, to figure out what's left over, I could take away that 39 for example, I might do $129 minus 39, and as I subtract, I realize there'll be $82 left. And by the picture, well, look, these two are the same bars. Ella and Terrence in these bars that equal the same amount of money. So I split 82 between those two bars, and I should get 41 and 41. Do those add to 121? Can I check? 41 plus 80. Yeah, it does add. And so I think I've solved it. But what was my original question? Terrence has blank dollars. Oh, okay, so up here, so 41 plus the 39 together would be 80. So Terrence has $80. And model drawing is just a way of using rectangles, really, and bars to think about a scenario. So, interesting. Let's take a look at how this could approach in some different ways. So, here is the next question. All right. Why don't you take a look at this number one, and if you can, pause the video and think about how you might set this up using a rectangle or two rectangles to try that out and give it a shot. Go ahead. All right, so let's try again. So first of all, with my answer statement, I know I'm looking for how many boys there are. My answer statement might be, there are blank boys. And again, I know I'm done when I can fill in that question. It means I comprehend the problem a little bit. And then it says there are 3/5 as many boys as girls. Well, again, I might do it like the last time. There's a couple ways to approach these. I might choose boys and girls. And if there's 3/5 as many, this is where we can set it up as a ratio question. You know, for example, just to show how this might look, I might draw bars where, again, there's 3 boys to every 5 girls. There's 3 out of the 5, 3 boys to every 5 girls in this classroom, because 3/5 are boys. And then it says, if 75 are girls, how many are boys? Well, let's go back. Well, I know this bar here is 75. And this has 5 equal chunks. So if I take 75 divided by 15, I'm sorry, it has 5 equal chunks, so 75 divided by 5 would be 15. And that means there'd be 15 girls in each of these chunks. But using a bar modeling, that's the key, because these 3 chunks up here are also the same size, because again, it was 3/5. So using that, it looks like there would be 45 boys going through. Now, it's interesting because you could also do this with model drawing using one bar. And let me show you. For example, because 3/5 are boys, I might just take a look and do a comparison. I could start with, there's lots of ways to do this, like, again, here's girls that are 5ths, and I know there's 75 girls, and 3 of those 5ths, boys are equal to 3/5 of the girls. So thinking about it like this, it's the same thing. I could take, if all the girls are 75, I could divide that into 5 equal chunks. And then, it doesn't mean that these are boys, it means that this is the same number of boys, but that 3/5 of it are boys, and that would be, again, 45. Interesting. So again, it's just this rectangle drawing chunking strategy that is used in many different ways. And let's try one last one. Try number 2, pause it. This one's only going to have 1 bar, by the way. Try this with 1 bar, and then come back and see how you approached it. Okay, give it a try. Okay. Well, first of all, did you start with your answer statement? So we know the final question here is how many pages were in the book. So just to make sure, I'm going to go ahead. The book has blank pages. And again, it makes us slow read, makes us realize what we want to solve for. So Evelyn here read 25 pages of a book on Friday morning. So first of all, this whole problem is about a book. So what we do is we just draw a rectangle. And this rectangle is my book. All right, that represents all the pages in the book. I go back, and it says she read 25 pages of the book Friday morning. Okay, well, again, I don't know how much that is, but it's okay. I'm just going to cut it off. This was 25 pages on Friday morning, F-I-M for Friday morning. Okay, so I'm just marking it up. She read 1/4 of the remainder on Friday afternoon. Well, what's the remainder? That was the remainder. And she read 1/4 of that. So looking at the remainder, I could break that into 4 pieces, and she read 1/4 of that Friday afternoon. So this piece here was Friday afternoon, but I don't know how much that was, right? I just know that that was Friday afternoon. And I know that these four chunks are the same because I cut it into fourths. And it says if she still had 90 pages to read after Friday afternoon, how many pages were in the book? So 90 pages were left. So she read this, and there was 90 pages left. Oh, that means these final 3 chunks were 90. So if I divide that into thirds, into 3 equal chunks, that's 30. But you know what? Wasn't that chunk here? That was the same as those chunks. Remember how we cut it into 4 pieces? So now I know that one. Oh, and that's it. Now, if I add these up, 25 plus, this looks like 120. So I think altogether that would be 145. The book has 145 pages. And so again, this is something we'll play around with in class from time to time, but just wanted to show a general problem-solving strategy called model drawing that, is a general strategy that can be used across many different content areas. And a homework coming up to try a few of those with your group. All right. So the last type of problem solving is teaching through problem solving. So when we think about teaching through problem solving, it's actually the exact opposite of the first one we did, of for problem solving. In this enactment, instead of starting with skills and giving a problem later, teachers start with an interesting, purposeful problem, and through looking at that problem, through thinking about and attacking it, students learn specific math skills and concepts through the problem. So it flips it around. So by starting with a problem, it could pique students' interest in an idea. It could allow students to use prior knowledge to think about how they might attack something or approach something. It might raise the need to learn some new math from which we could learn some new math skills and concepts after we started with posing a purposeful, well thought out problem. So when I think of that, I can think of this quote by Hebert in 1996 that was kind of talk about what this meant. And he said, allowing the subject to be problematic means allowing students to wonder why things are, to inquire, to search for solutions, and to resolve incongruities. It means that both the curriculum and instruction should, and there's the word, begin with problems, dilemmas, and questions for students. Interesting. So again, beginning allows the subject for students to wonder why, to wonder what we could do, to think about, to search for methods and solutions to go through. So in teaching through problem solving, it just means starting with questions that students might be able to work on without getting taught all the, the algorithms of math first. For example, if we were dealing with students who were starting fraction division, instead of teaching fraction division right away, we might start with a question they could dive into, like this one. You have a recipe that makes 6 small biscuits. The recipe calls for 1/4 cup of sugar. If you have 2 cups of sugar, what is the most number of biscuits you can make? Now with students, within drawings or different types of manipulatives, they could dive in and try and make sense of this situation, to try and get ideas of how many biscuits they think they could make. So tell you what, how would you use a visual drawing solution? Can you draw some biscuits here? What does this look like for you? Go ahead and pause the video and think about what the work you might expect a 4th, 5th grader to do that was working on this question. So go ahead and pause, give it a shot. All right, well, let's take a look. So is again just this idea of just trying to make sense of something. So I have a recipe that calls for 1/4 cup sugar, and I have 2 cups of sugar. So I don't know, there's lots of ways you could draw this. This is where it's kind of fun to see different approaches. Maybe I just draw some cups of sugar. So that's 1 cup sugar, and there is another cup of sugar. And it says that 1/4 of a cup was needed for a batch. So maybe I could split these cups into 4 pieces, and you can cut them into fourths many ways. So that would be fourths. Oh, so interesting. So look, so if each of those represents a recipe, I can do 4, 5, 8 batches. I can do 8 recipes here. And how many was in each recipe again? Each recipe could make 6 small biscuits. Oh, so like this amount of sugar, that's 6 biscuits I could make with that. 6 with that, 6 with that. So each of these squares represents a batch. And so, oh, cool. It looks like that's 24 plus 24. I could make 48 biscuits. I think, with that sugar. And there's many ways we could have drawn this out. Hopefully you gave it a shot and see how you did it. But then what we can think about is, and again, students might have solutions for it. Some may have not gotten there. Others have some different ways of thinking about it. And this is great. And we can start with a problem and then think about as well what we just did. That when we began this, we realized we had 2 cups of sugar, and we were wondering how many quarter cups went into it. And so when we think about the math we just did here, this is what it looks like as a math problem. There was 2 cups of sugar, and I wanted to know how many quarter cups went in there. And if we look at it, I saw that I could make 8 of those amounts. And so we start to see, this is what fraction division looks like. How many 1/4 could I make out of 2 cups? And I can see visually the answer is 8. And I'm not starting with a rule or procedure. I'm starting with the idea of trying to make sense of what this actually means and what it looks like. And that might be an example of starting with a problem that dive into the thinking about what it means to divide by a fraction. Another example could be an example where maybe we're thinking about factors in the classroom. And we give kids this question. But again, we don't need to start by talking about factors and definitions. The point here is we start with a problem. We could say Kathy has 36 bracelets to sell in her store. She wants to display the bracelets in rows on a shelf. Kathy wants to have the same number of bracelets in each row. And ask the kids, okay, what are at least 4 different ways Kathy can display the bracelets on the rows on the shelf? And we can even give them manipulatives, to cubes or things that could be bracelets. And to think about this, they have to be nice. So they have to have nice rows, equal rows to go through. And you might realize, for example, you could do, 6 rows of 6. That works. Or you could do 9 rows of 4. That works. Or 2 rows of 18. Or 18 rows of 2. Or even 1 row of 36 if we wanted a really long row. But the idea is as we play around with ways to break 36 into groups of equal rows, we start to realize that all these numbers basically divide nicely into 36. And it's something, a discussion comes out about how we can think about what numbers worked and what numbers didn't. And all the numbers that made nice equal rows were numbers that divided nicely into 36. And these are called factors. It creates a need for a definition and creates, again, through the problem, we can start defining how to think about the math that lies beneath it. So in conclusion of these 3 methods, here's the 3 things all back to back. We see that, again, the top one, teaching for problem solving, is this the exact reverse of teaching through problem solving. And the middle one, the about problem solving, is really, it's more nuanced because it's not about specific math concepts, it's about general problem solving strategies, learning about being a good problem solver. So tell you what, here are 3 scenarios. I believe that you could argue that one of these would be best categorized as about problem solving, one as through problem solving, and one as for problem solving. Take a moment, pause the video, and write down which one you think best characterize each of those 3. Go. All right, well, let's see if you agree with me. Here's what I think. I think the first one is an example of about problem solving. And the reason is focus here is about a general strategy of decomposing numbers that can be used on all kinds of content. So it's a general strategy they're adding to their toolbox that they can use in a variety of different questions across many different mathematical units. So that's why it's an about. The focus is not on math concept, but about a general strategy. Number 2, I would argue teaching for problem solving because, again, it says the kids are reviewing a skill they already have, and then we're giving a challenging word problem using that skill and had to work in pairs to make sense of it. So they're using math they already knew for a problem now. But the last one would be through, because the teacher here is getting at the idea of median and mean, but they don't start with that. They don't start with definitions. Instead, they start with a scenario about maybe in the class, the principal asked the class to say how many typical pets a 5th grader has. And so when trying to think about, well, geez, how do we pick one number for a typical 5th grader? Maybe they take a quick poll in class and look at the numbers and debate which number they should report. And through that discussion, they realize there are some mathematical ways, often called the mean, median, and mode, that can be used to choose one number to write a data set. But again, through that problem, the mathematics was arrived at and taught. So hopefully that makes sense. But here's some key questions I want to stress. One is, if you go out to the field and you sit and observe a math lesson, Do you think every lesson could be categorized as for, about, or through problem solving? Correct answer here is no, definitely not. Because these distinctions only occur in classes when problem solving is actually happening. If the classroom is really just kids doing exercises, right, and which again, I'm not saying is bad, we need that, just practicing a method, teachers showing them how to do something and then practicing, we already agreed that's not problem solving. So that would be a lesson on more direct instruction, a lesson about students, again, on a procedural focused lesson, but not problem solving. So these three distinctions only happen when a class is engaged in problem solving, which again, some classrooms is not that frequent, unfortunately. The second question I have here is, when considering these three distinctions, is one of these better than the others, or is one bad and one good? Is there a ranking of what we should do as teachers? And here's my 2 cents. I believe any problem solving is good problem solving, right? So I think there's a time and place for all of these that can be used, and there's kind of you could argue different ones are more appropriate at different times, but let's just agree that in getting kids to be good problem solvers, that all problem solving is good problem solving. Now, that's my 2 cents. Now, in the book, you're going to notice that our author does really stress through problem solving as a preferred method. And he has reasons, and you can read those and think if you agree with that. But I just want to say in general, this isn't about one being, in my mind, totally better than the other. It's understanding some choices and thinking about different approaches we could use at different times as teachers to meet the goals we have for our students. So that's the big idea here in Chapter 3. Now, I want to give a quick nod to something that we're going to spend a lot more time on actually next semester in the follow-up course, CI 432. But just as we begin the semester together to think about, so what if I wanted to teach a problem-based lesson in a classroom? How do I start thinking about this and investigating this? Well, in the Chapter 3, you probably will notice that the author just talks about a 3-phase lesson model, which is simple, and I love that it's simple, but yet it's profound. When we really do it well, it can change our instruction and really make lessons work a lot better when we do this thoughtfully. And our author calls it before, during, and after. Some other textbooks call this launch, explore, summarize. I'll use those interchangeably. But the idea is before, or the launch, students have to make sure the problem is understood and establish expectations for their work and in partners and the time they have, make sure that any prior knowledge is activated they need to have to dive into this question. And then in problem solving, there's this notion of explore. Teacher needs to let go, and students are working individually or in pairs or in groups while the teacher is supporting and observing and listening, scaffolding, extending during this work time. And then in the after phase, when the teacher decides the work period is done, there's a community experience where students are sharing their ideas, or teacher is summarizing what they saw, orchestrating discussion, solidifying ideas, introducing new ideas. And this is how we can think about teaching that. So to put some skin on that, let's think about a very quick mini lesson for maybe a first grade class, or even a kindergarten class, just to think about some basic addition skills, part whole addition. And this has a bird analogy here. So let's suppose we wanted to build a lesson around this problem. There are 2 trees, an oak tree and an apple tree, and 7 birds. How many different ways can the birds choose to rest in the 2 trees? So if I was a teacher and I say, hey, this is kind of a neat idea, I think the kids, this could be a good one for them to wrestle with, all the ways to make 7, and has a nice context they could use as well. Well, in a 3-phase lesson plan, I would start thinking about, well, what am I going to do to make sure they understand that? Well, what I might do, and this is just, again, there's no right answer here, but just to think with you, in the before phase, I might think, well, I'm going to start getting them interested and ask them what kind of birds they've seen outside their house or the school, or when they've gone to the park, and just start a discussion about birds. And then I'm going to pose the scenario about our 7 birds and 2 trees, that they want to take a nap in these 2 trees, and they're trying to figure out where they each want to nap. And our job is to figure out all the different ways they might choose to pick the trees to nap in. And to clarify that, maybe I decide on my smartboard, I want to, I'm going to shrink my screen down just for a second, to come up and have one student be an example and choose how they want the birds to nap in the trees. And maybe that student chooses to put 3 birds in the oak tree and 4 in the apple tree. And of course, I can have my students tell me that, answer the questions. And then I'm going to tell them that to keep track of the napping birds, we're going to use our chart. Each kid is going to get a chart. And so for example, they might write there was 4 birds in the apple tree, and I should have aligned the apple and oak tree in the same order as the worksheet. When I made this slide, I didn't think about that, but that stuff matters. It would be better to have the graphic organizer aligned with the worksheet, so sorry I didn't catch that earlier. And the oak tree, there was 3. But then what I want them to do, and talk with me, maybe this is where this is teaching for problem solving, we've already done some addition, but I want them to think about what the number sentence would be, that if there was 4 birds in the apple tree plus 3 in the oak tree, altogether that would make 7. But then I might have another student come up and ask them how they might do it. Maybe we realize we could have 2 birds fly over here, and now there's 6 in the apple tree and 1 in the oak tree. And in the launch, I don't want to solve too much, but I'm just giving them a little bit of a start. They're clear on the directions, on the expectations of how to use the sheet and how we can move the birds around. And then maybe I can set expectations that they're going to be getting some Unifix cubes and a little piece of paper that has 2 trees, and they're getting a graphic organizer, and they have a partner that they can talk with, but I still want them to do all their work on their own paper, but their partner can be helpful to go through. And once I'm sure they're clear, I set them off to the during. Now the kids are working on this, and they've got their cubes and their trees and their charts, and of course I'm walking around, I'm listening, I'm observing. I might ask students to explain, hey, what does this number sentence mean? Can you tell me what does 6 plus 1 equals 7 tell you about the birds? What did that mean to you? I might look for strategies for students that are taking an organized approach and ask them to tell me what they're doing there. Why are they approaching it that way? And if a student says, I think I got them all, I'm going to ask them, how do you know you got them all? Are you sure? Might want to check with your partner, or is there a way we could think about how to make sure we have them all? And if I think a student, has gotten to the point where they are done, but the rest of the class isn't, I might extend their thinking and ask them, I might give them 2 more blocks and say, okay, well now you have 9 birds, and here's a new organizer. Try that with this one. How many ways do you think there are for this one? And then when I deem kids are ready, we can come back to the after phase as a whole group, come back together. And I might have students start out by telling me how many different ways they found the birds could nap differently in the trees. And kids probably won't agree in first grade. I found 7 ways, I found 8 ways, I found 10 ways, and we can I can invite a student to bring their graphic organizer up to the document camera and maybe show us what they found and see if the kids think that's all the ways, if there's other ways that they're missing. And maybe I saw a kid who used a really good strategy to organize to make sure they had all the ways. And we might have that. I might invite that student to share their paper to show how they organize their work in a logical way. And maybe then we can make a list on the board of all the ways to make 7 together, just to solidify that idea. There's many ways to break apart 7, and we could put all the ways on the board. And then maybe for homework or a follow-up activity or the next day, we might repeat the same thing for 10 birds just to go through. And so this 3-phase lesson model is, I believe, a really key idea that when we plan well using this simple structure, it can really go a long way to making effective lessons. And I'm just going to say again that next semester is more our pedagogical time when we practice lessons and build these and go through, but this still will be a big idea this semester. So let's close out the video. So in closure, let me fix this letter right there. So in closure, well, problem solvers, of having kids persevere and making sense of problems. That's only going to happen, first of all, when we're actually giving real problems and helping give them the tools to be good problem solvers. It doesn't happen just on its own. Some classrooms it's not happening very much. And this takes intentionality with our approach, with our types of problems we're choosing, with, again, the way we think about planning our lesson. And again, this course will explore a lot of that. And so with that, that ends video 1. And until next time, all right, have a good one.